Good morning to all of you who came. We're in our last day of the DDD, so I would like, first of all, just to say thank you for all our tour organizers during the conference. We had 8 tours yesterday, full people. To summarize the conference, we had over 800 participants from 50 different countries. And it's really been, I think, inspiring and a good experience for me, at least. So thank you very much for coming and being here. I must thank 4 people that I would like to thank them. They're not here. But I have to thank, first of all, Dorit, the producer of the event, Esther, who was a great help, and I think most of you who came from abroad at least are in direct contact with Esther for all her help. Kochi Abu Aron for the help also, and Ilana Seller, our institute secretary, who did invaluable help. So I have their thank you gifts soon. And then I'm very, very proud now, our keynote speaker, Professor Ehud Meron, who agreed just from one day to another to give a talk. This is something that is really special for us. So we understood that our keynote speaker who didn't come on Monday could not come, and he said on Zoom, so I said no Zoom. And we were thinking, I was just trying to decide quickly who is something that will be a broad interest and that really can fit as a keynote in such an important conference. And immediately the first name was Professor Ehud Meron. I'm really, really proud. So please have Professor Ehud Meron. Thank you very much.
Good morning. Thank you for the introduction. I wish Henry a quick recovery, and I'm glad I had, and I'm glad I was given the opportunity to replace him and I'm glad I could on a short notice. The question that I would like to present here, or to study, or to address, is a major question in ecology, but I would like to present here a physicist approach to that question. That question is how does an environmental stress affect ecosystem function? And that question can be split into 2 sub-questions. First, how do ecosystems respond to environmental stresses? And then how that response affects the functioning of ecosystems. Now, the response of ecosystems to environmental stresses can occur at different levels of ecological organizations, starting with the phenotypic changes at the level of a single plant. Plants, for example, can deepen their roots in order to reach moister soil layers. There are, at the community level, community shifts may occur, for example, from fast-growing species to stress-tolerant species. But there is another class of response mechanism at the population level, which is special self-organization in periodic patterns. Here we see a beautiful example of so-called fairy circles in Australia. These are grasslands with barren gaps, circular gaps of bare soil. And this is a kind of mechanism to cope with water stress because the remaining plants benefit from an additional source of water, which is the water they draw from the bare soil patches. Now, the response of these mechanisms, or these mechanisms that occur at different organization levels, are likely to act in concert and interact with one another, because if one mechanism acts to relax the stress, then it eliminates the driving force for another mechanism. So this is the type of interactions that I want to address here. Interaction between phenotypic changes and spatial self-organization, and between community reassembly and spatial self-organization. And I'll do that in the context of dryland vegetation, subject to water stress, using mathematical models. So this is our lab, the models that we develop. So I'll start with a brief review of spatial self-organization of dryland plant populations, or what we call vegetation pattern formation phenomena, and include some helpful concepts of pattern formation theory. And then I'll proceed to cross-level responses, starting first with the interplay between phenotypic changes and pattern formations, and then between community reassembly and pattern formation, and then I'll conclude. Now, special vegetation patterns is a widespread phenomenon in drylands, and they show a wide variety of patterns that are familiar from other contexts. Some of them you are obviously familiar. Some of them are you may not. For example, these stone patterns in Arctic regions. What we see here is an example of fairy circles, but not in Australia, in Namibia. It's the same type of phenomenon. The local processes may be different, but the pattern is similar. Here we see, so this is what we call it a gap pattern. These are spot patterns of woody vegetation in Zambia. These are stripes of acacia trees in Australia. These are labyrinthine patterns, which look very similar, but the scale is completely different. This is grass with a typical length scale of 10 centimeters, and this is woody vegetation with a typical length scale of 100 meters, 3 orders of magnitude difference, yet the type of patterns are similar. And we have other type of pattern rings, which are seen with many clonal species, vegetation spots, isolated spots, and actually spots within spots, and more exotic patterns like arcs and spirals. Now, pattern formation theory tells us that spatial patterning is often driven by positive feedback loops that amplify non-uniform small perturbations, which drive the system to a different state, which is spatially non-uniform. So what feedback loops can drive vegetation pattern formation? General feedback of this kind is local vegetation growth that drives water transport towards the growth location, which further enhances the local growth. So with this feedback loop, we can understand why uniform vegetation can become unstable to the formation of patterns. Suppose we have a uniform vegetation, like here, and by chance we have a patch of denser vegetation. That patch draws water from its surrounding more than the surrounding does, so there is a net water transport towards the denser patch, which helps it grows yet denser, but at the same time inhibits the growth in the surrounding because it takes water from the surrounding. And this a mechanism of patch formation, basically. And this is called a scale-dependent feedback because it consists of positive short-range interactions within the patch and long-range inhibition. This feedback loop induces an instability of a uniform vegetation to periodic patterns. And here is just a simulation to show how these patterns develop. And the generic pattern that developed is a gap pattern very similar to those fairy circles examples that we've seen. Now, there are several mechanisms of water transport. Overland water flow, water conduction by laterally spread roots, and saltwater diffusion. Which water transfer mechanism applies depends on the type of system. For example, if bare soil, in many cases, bare soil tends to be covered by soil crusts, which can be physical but also biogenic. These crusts reduce the infiltration rate into the soil, but they cannot develop in vegetation patches. For example, one microorganism that forms this crust are cyanobacteria, and it needs sunlight for growth, which is doesn't get much in a vegetation patch. This creates infiltration contrast, low infiltration rate in bare soil and high in vegetated soil. The root system contributes to that effect because it makes the soil more porous. And this differential infiltration induces overland water flow towards the vegetation patch. And as the patch grows further, that contrast increases, and then, therefore also the overland water flow is faster. Other mechanism is lateral water transport. As the plant grows, the root system extends in size, and the water uptake is larger, higher. And with saltwater diffusion, that mechanism applies to, for example, to sandy soil, where the infiltration rates are high everywhere, also in bare soil. But then the uptake of water in the root zone deplete the water content there and create saltwater gradients and saltwater diffusion towards the location of the plants. A mathematical model that captures all these feedbacks is this one, but I'll skip that and show you results obtained with models of this kind. And the results that I'll show you actually apply to all three transport mechanisms, and other models that have been proposed show similar results. Now, what I'm showing you here is a bifurcation diagram. This is a new concept that I want to introduce here to this audience, which is very helpful in understanding the solutions which represent states of the system, different states of the system. So in that diagram, the horizontal axis is some parameter. In our case, it's precipitation rate. And the vertical axis is some state variable, can be biomass, water in that case. And we take either the spatial average of it, or we can take the maximum biomass. It doesn't really matter. What we want is to distinguish between the different solutions. Each curve here represents a different solution, namely a different possible state of the system. The convention here is that solid lines represent stable states. Stable states are states that if you perturb them, disturb them, then the perturbations decay and the state is recovered. And dashed lines are unstable states, okay? So we have this horizontal line at biomass equal to 0, which represents a bare soil state. It is stable up to some critical precipitation, but beyond that, it is unstable. So here, seeds do not germinate, while here they germinate and grow. it becomes unstable at a point where a uniform vegetation state appears, this black line, but that state is stable only at high precipitation. As precipitation is decreased from high values, that state is losing stability to the formation of periodic patterns, like the mechanism that I motivated before. And so this is, the red line is a periodic pattern. For example, periodic pattern in space, like this one. It is stable to some range of precipitation, but then it loses stability to another pattern with double period, double wavelengths. Basically, every second patch disappears here compared to this one. But there are other solution branches of periodic solutions, and as precipitation decreases, we have solutions of longer and longer wavelengths. So this is what this diagram tells us. These are stationary solutions that the system approach in the course of time. And the point that, an important point that this diagram demonstrates is that those periodic solutions, periodic patterns, extend to precipitation values much lower than the uniform vegetation state. So, and in this sense, they are a mechanism to cope with water stress. And the reason is that in a periodic pattern, each vegetation patch benefits also from the water it draws from the bare soil neighborhoods. And this compensates to some extent for the reducing rainfall. And this is why those periodic patterns persist to low precipitation values. This was the bifurcation diagram of solutions in 1 dimension. In 2 dimensions, we can have different morphologies, the gap patterns that we've seen, and then stripe patterns and spot patterns as precipitation decrease. Any of these patterns can show different periodic solutions with increasing wavelengths as precipitation decreases. So we have here a wide variety of patterns, and actually there are even much wider variety because there are precipitation ranges where 2 and more different patterns are stable, or different states are stable, which means that we can have special mixtures of different patterns and a variety of disordered patterns. But what I want to stress here is that there is a generic universal sequence of patterns along the rainfall gradient, hexagonal gap patterns that as precipitation decreases transform to a stripe pattern and then to hexagonal spot pattern before collapse to bare soil occurs. And these patterns are seen in nature, as we saw already. It is remarkable that to date there is no experiments that demonstrate in laboratory experiments, in greenhouse experiments, this sequence of states. The reason is that it's very hard to conduct such experiments because the timescales are very long, and as Osvaldo mentioned, PhDs are 3-4 years. This requires more than that. But there are now new attempts. So far for the introduction of pattern formation theory, and let's proceed to cross-level responses and start with the interplay between spatial self-organization and phenotypic changes. And here, and focusing as a case study on the Namibian fairy circle example. So here is the pattern Namibian fairy circles. We have these gaps of bare soil, and the vegetation matrix in between is pretty uniform, fully covers, covering the soil. Now, we would expect, according to the model predictions, that as precipitation decreases, we should see stripe patterns, transition to stripe patterns, and possibly to spot patterns along the rainfall gradient, and these patterns persist but what is fine, despite the fact that those first cycles occupy really wide ranges, wide areas where there is a rainfall gradient, we don't see stripe patterns and spot patterns. What we rather see is spatial patterning at small scale within the vegetation matrix. And our hypothesis is that as precipitation decreases, a phenotypic change takes place from shallow root plants to deep root plants that reach a moister and more compact soil layer. So to test this hypothesis, we extend the model to include the depth dimension by considering two soil layers, which is in accord of field observations in these areas. A top layer consisting of loose sandy soil, about 20 centimeters deep, and a deep bottom layer. Within the top layer, because it's loose, soil water diffusion, soil water conduction is fast. In the bottom layer is compacted soil with slow, short-range soil water diffusion. And these have been verified in experiments carried by this group, Kramer et al. Now we define the two phenotypes according to the layer from which they take up water. So shallow root plants take water from the top layer only, and the deep root plants take water from both layers. And we further assume possible phenotypic transitions. Shallow root plants transform into deep root plants when the water content in the bottom layer is higher than in the top layer. And again, this is a pretty general behavior that sometimes is called hydrotropism or hydropatterning. Now, here I show model results, but the top row is for the case where the switching rate between the two phenotypes is 0. So we have only shallow roots phenotype. And then what we see is the classical sequence of sets, gaps, stripes, spots along the rainfall gradient. But when we switch on transition between the two phenotypes, we get gap patterns, but as aridity increases, we don't get strides, but rather we get small-scale patterning within the vegetation matrix. And the reason is that by that time that these gaps develop, also phenotypic transitions to deep root plants occurs. And the deep root plants probe the bottom layer where the soil is compact. Diffusion, water transport, water diffusion occurs on a short scale, and therefore this dictates short-scale patterning rather than long-scale patterning. And actually what happens is that the large-scale pattern is freezed because all the dynamics go to the short scale within the matrix, which cannot affect these are small short-scale processes that cannot affect the large-scale behavior. And if we further decrease precipitation, then vegetation within the matrix dies out, leaving vegetation rings before collapse to bare soil occurs. And this is what is seen also in empirical images, the same type of behavior. Now, there is another important result of this study, which is that that response that involves both mechanisms, spatial patterning and phenotypic changes, leads to significantly higher resilience to droughts, to drier conditions. What we see here in these simulations, the collapse, as we further decrease precipitation, these spots collapse to bare soil at 123 millimeter per year, but these rings collapse to bare soil at 46 millimeter per year. So there's a dramatic increase of resilience. So what we see here is basically an alternative response pathway to drier climate of higher resilience. And this is just because we included another element of ecosystem complexity, the possibility of phenotypic changes. And I'll come to that later on. Okay, let me go now to the interplay between spatial self-organization and community reassembly. And here I want to use a trait-based approach to community dynamics, where we focus not on species, but rather on functional groups of species that share similar values of some selected functional traits. And the traits that we consider are plant growth, that controls the capability to outcompete other species by growing taller and capturing more light, and mortality, that controls the capability to outcompete other species in dry conditions by better tolerating water stress. And we assume a trade-off between these two traits and define a trade-off parameter normalized to the unit interval. So chi equals 0 represent fast-growing species, chi equal 1 represent stress-tolerant species. And the community is then described by a biomass distribution both in physical space and in trait space along this trade-off trait axis. And a typical biomass distribution in trait space is shown here. It's a unimodal hump-like distribution. And that distribution contains at least 3 community-level properties. The position of that pulse-like shape along the trade-off axis, which we quantify by chi-max, its maximal value represent the composition of the community, whether it's closer to stress-tolerant or to fast-growing. The width of the distribution defines the functional richness or functional diversity. And the area under this curve is the total biomass. And now we can study these community-level properties varying any parameter that we want, initial conditions, mimicking various scenarios in real systems. And another way to present these results is to include the information about spatial distribution. So this is the horizontal axis is the physical space, the vertical one is the trait space, and biomass is represented by the green color. Darker color represents higher biomass values. Yellow is bare soil. And so here we have a uniform vegetation, and here we have a pattern vegetation. And also here we want to derive a bifurcation diagram, but now of community states. And so the vertical axis, the horizontal axis is as before the precipitation, and the vertical axis is the composition measured by chi-max, going from fast-growing species to stress-tolerant species. That solution branch represents a spatially uniform community. And it is stable at high precipitation and loses stability as precipitation drops below a critical value. And here periodic patterns develop. But the point that which we are represented by these lines, But the point I want to stress here is that while the state is spatially uniform, the vegetation uniformly covers the land, there is a shift from fast-growing species to stress-tolerant species. The curve is going upward as precipitation decreases. Once the instability to periodic patterns develops, we have a transition. I mean, the system can no longer follow this unstable state, so it converges to the alternative stable state that exists at the same precipitation value. It converges to a periodic pattern. This involves a partial reversal in the community structure to fast-growing species, because now species at the same precipitation, now species benefits from another resource of water, the water they draws from the birth soil surroundings. But the point that I want to stress here is that that line is pretty horizontal, meaning that although precipitation decreases, community composition remains unchanged. And this is a kind of homeostasis. It remains unchanged despite the fact that the precipitation decreases. It's like our body temperature that remains constant irrespective of the environment where we are. And this homeostasis is due to the fact that as precipitation decreases, there is repatterning occurs. So we start with a periodic pattern of some wavelengths. As precipitation decreases, that periodic solutions with the same wavelengths keeps on, but the patches become thinner. And as a result, they benefit from larger surrounding bare soil areas, which compensate for the decreasing rainfall. So there's water availability remains more or less the same. And as we further decrease precipitation, this thinning is no longer effective, and there is a transition to a longer wavelength patterns. It's a patch dilution. Every second patch dies out. And again, here, those patches benefit from wider, larger bare soil areas, which compensate for the reducing rainfall. So this is why that line is pretty horizontal, because water availability remains more or less the same. If we further decrease precipitation, at some point this graph goes up, and we have collapse to bare soil. Another result is that we have, as we see here, we have precipitation ranges of bistability, meaning that there are two alternative community states that are stable and therefore possibly realizable: uniform vegetation and periodic patterns. These two stable branches overlap. Okay? In these ranges, we can have localized patterns, like we can have uniform vegetation with domains inside of patterned vegetation. And these domains can be of any size. And these are stable states. These domains do not expand nor shrink. These are stable stationary states. And the patterned domain provide a different niche than the uniform domain, because in the pattern domain, there is more water availability is higher, and therefore it can host faster growing species compared to this one. So if we plot the biomass, the distribution of biomass in the trait space, we can get a bimodal distribution and a much larger functional diversity. Okay? And this may be on ecosystem management, for example, managing grazing non-uniformly in space in certain areas to create pattern domains. It also bears on resilience in drier climates, as we have here two mechanisms that to cope with water stress that act together. Let me conclude. Well, this was faster than I thought. The consideration of phenotypic changes along with spatial patterning resolves two outstanding puzzles in the study of Namibian fairy circles. First, the observation of Shimon, it will take me a while. Observation of multi-scale patterns. This actually has been pointed out a few years ago by the Princeton group, Tarnita et al. In a Nature paper in a Nature paper where they point out that those fairy circle patterns can be multi-scale. The large-scale gap patterns and the small-scale patterns within the vegetation matrix. Thank you. But in order to explain that, they resorted to an additional agent in the system, termites. What we show that we don't need that additional agent, and that is good because although termites are observed in fairy circles in some areas, there are other areas where we have those gaps or fairy circles without indication of termite activity. So the termite hypothesis, in my opinion, is not consistent with at least some observations. But here we show that we don't need it. I mean, we just need to take into account more elements of ecosystem complexity, like the tendency to hydrotropism or hydropatterning. The other puzzle that this study resolves is the absence of large-scale stripe and spot patterns, as we discussed. And we found that phenotypic changes plus patterning increase resilience in dryland climates. We saw that the consideration of community reassembly along with spatial patterning leads to new insights such as the homeostasis of community compositions and bimodal distributions. And the bottom line is that taking into account more elements of ecosystem complexity. Ecosystems are complex systems. This complexity exists. We just, in modeling, we try to simplify the models and eliminate them. But when we take more and more elements of ecosystem complexity, we find that there are many new pathways of response to environmental stresses. Some of them may lead to tipping points, but some may avoid them. And this brings me to a new project that we are about to start in a few months, which will be funded by the ERC, where we want to study this pathway of resilience and evasion of tipping and extend the biomes to savanna and tundra. And this we do with an interdisciplinary group of people consisting, in addition, Max Rietkirch from Utrecht University, Arjen Dolman, who is a mathematician from Leiden University, and Ayla Meyer-Smith from Edinburgh University. She's studying tundra. And with this, I want to conclude thanking my collaborators, Omer Tsuk, a former PhD student, Jamie Bennett, a former postdoc, Bidesh and Mitchell, current postdocs, and my colleagues, Stefan Getzing from Göttingen University, and Chezi Yitzhak from here, BGU. And here are some relevant references, and I'm ready for questions if there are. And thank you for your attention.
So thank you very much, Ehud. Any questions, comments? Yes. 1 minute. I just need to come to you, because otherwise they won't hear it when it's recorded.
So another mechanism that gives rise to spatial pattern is allelopathy. So exudation of compounds to below ground to keep out other plant roots of the same species. So another way in which you get pattern formation. Of course, that requires
The allelopathy. Exudates between roots is another way to do.
And so that obviously has implications for nitrogen availability, which obviously one of the major sources of nitrogen is going to be coming from the precipitation. I'm wondering, particularly as you're going into different ecosystems, that sort of thing, something to consider that's just not. Yes.
Yeah, that'd be great. Other questions?
Okay, thank you for talk. It was really nice to me. Yeah, so one of the assumptions of your model, there is a fast-growing and stress-tolerant. It's not necessarily the same species. Fast-growing and it's not necessarily the same species. Can you elaborate or clarify to me?
Well, I mean, whether a single species can change or show phenotypic plasticity and switch from fast-growing to stress-tolerant behavior, tolerance behavior, or, for example, by closing stomata or things like that. This is basically a matter of interpretation. So in the model, we could consider different species or functional group of species, or in principle also different phenotypes. So it depends on the context. And to the level of that model, the level of simplicity, that we can treat both cases in the same manner. If there are differences, then we will need to consider other models or further develop it.
So thank you very much. Yeah, so now we have 10:15. There is the other sessions. So please, you're welcome for coffee and refreshments. Thank you.